Further Algebra Lesson 3, Binomial Expansions where the first part of the binomial is not 1. So in the last couple of lessons we have been using the general binomial expansion which we can use with any value of n. Now what we've learnt so far is that if n is a positive integer then this expansion is valid for any value of x. We also know that the series expansion is a finite summation of terms if n is a positive integer. Now, in the last few lessons, we have also used this generalised expansion for values of n which are either negative or fractional or possibly both. We have seen that in these cases, the expansion results in an infinite series of terms and is only valid for certain values of x. Now, in every situation where we have used this expansion, our binomial has always started with a 1 here. We have completed examples where it's not just x in the second part of the binomial, we've had 3x or negative 7x or 2x squared as part of the expansion. That's absolutely fine because all we do is replace x with whatever is inside the bracket in the second part. But we have never done an expansion with anything other than 1 as the first part of the binomial. So in today's lesson, we're going to learn how to deal with expansions where the first part is not equal to 1. So let's look at our first example. We're going to find the first 4 terms in the expansion of 2 plus x all raised to the power of negative 1. And the first thing that you need to immediately be aware of is that the start of this binomial is not 1. Now, we can deal with this by making use of a very simple factorisation. So I'm going to put in a big set of square brackets, which is purely for clarity. And inside the brackets, I'm going to take the 2 plus x, which is all being raised to the power of negative 1, and I'm going to factorise out a 2 like this. Now this means, in the brackets, I've got 1 plus x over 2. Now look at that green result there. If you expanded that, you would get 2 plus x, and then the whole thing is being raised to the power of negative 1. So this is a perfectly valid piece of algebra here. The next thing I'm going to do is I'm going to raise both parts of this to the power of negative 1. So the first part, this 2 here, is simply going to become 2 to the negative 1. And then that's going to multiply by 1 plus x over 2 all to the power of negative 1. So I've simply taken the contents of the square brackets and I've raised each part to the power of negative 1, even though I haven't done the full expansion for the green part yet. Now, what does 2 to the negative 1 equal? Well, it equals a half. So I have a half multiplied by 1 plus x over 2 to the negative 1. And notice we now have 1 where we want it to be inside our binomial. And the other part of the binomial, which is here, well, this can be anything. Because remember, we just substitute the anything into our generalised binomial expansion. So all we now have to do is expand 1 plus x over 2 all to the power of negative 1, well, find the first 4 terms of this expansion, and then multiply this by a half. So let's do the expansion. So I'm going to expand 1 plus x over 2 all to the power of negative 1. Here's my generalised binomial expansion, but notice instead of x, I'm going to replace x with x over 2 in each term of the expansion. So let's do our expansion. Now it's important that we identify the value of n, which is of course this index here, so n is equal to negative 1. So let's start evaluating this expansion. So our first term is of course 1. And then we've got plus nx, so that's n, negative 1, multiplied by our x replacement, which is x over 2, plus n minus 1, which is going to be negative 2, multiplied by x squared, which in this case is x over 2 squared, all over 2 factorial. That's our third term, and then our fourth term is going to be n minus 1, n minus 2, all multiplied by our x replacement cubed, all divided by 3 factorial, ... Now, we're then going to simplify this using a calculator very carefully. Remember, if you're dealing with something like x over 2 all cubed, this is x cubed over 8. And of course, there's further simplification of that term to follow. Let's work this out. So this gives us 1 minus x over 2 plus x squared over 4 minus x cubed over 8. But remember, this is only the green part of this expansion, 1 plus x over 2 to the negative 1. To give us the true answer, we have to remember that there is a factor of a half as well involved. So we can say then that 2 plus x all raised to the power of negative 1 is equal to a half multiplied by 1 minus x over 2 plus x squared over 4 minus x cubed over 8, if we're just looking at the first 4 terms, of course. And this then gives us a final answer of a half minus x over 4 plus x squared over 8 minus x cubed over 16 for the first 4 terms. Now we're going to finish off by looking at the validity condition, which we can pick up quite nicely from here. If we look at the contents of the bracket, we can say that mod x over 2 has got to be less than 1, which then simplifies to give us mod x must be less than 2. If we multiply both sides by 2, or if you prefer, x has got to be between negative 2 and positive 2, which you can relate back to the original question over here as well. So let's look at a second example. We're going to find the first 4 terms in the expansion of 4 minus 3x all to the power of a half. So think about what we did last time. I'm going to set up my large square brackets, purely for clarity here, where the 4 minus 3x will be inside these large square brackets, so everything has to be raised to this power of a half. Now, I'm going to look at the fact that at the start over here, we have a term which is not equal to 1, and we want to turn it into 1. So I'm going to factorise out a 4 like this, and then the brackets will be 1 minus 3/4 of x, like that, with everything raised to the power of 4. Do a quick check back in your head with the green bracket, do an expansion, check that it multiplies back to give you 4 minus 3x. Now, we're going to raise each part of this to the power of a half, so that means that this 4 here is raised to the power of a half, and then we have 1 minus 3/4 of x also raised to the power of a half. Now, what is 4 to the power of a half? It's 2. So we have 2 bracket 1 minus 3/4 x raised to the power of a half. So we simply have to now perform a binomial expansion with the green part and then make sure that we multiply each of the terms by 2. So I'm going to move over here and I'm going to take the expansion of 1 minus 3/4 x to the power of a half, and we're going to perform this expansion. Our value of n is equal to a half, so we are ready to conduct our expansion. So our first term is simply going to be 1, and then we want to add on n, which is a half, multiplied by x. Now in the context of this question, x is being replaced by negative 3/4 x. So this is 1 plus nx, so I want here negative 3/4 x. I then want plus n minus 1, our x replacement all squared, all over 2 factorial, and then our fourth term, n minus 1, n minus 2, x cubed, all over 3 factorial. Now, let's simplify each of the terms carefully using a calculator. So here are our first 4 terms. Now, don't forget that we had this factor of 2 as well to deal with, so we know that we need to multiply each of these terms by 2 if we're going to get the full answer. So we can say that 4 minus 3x all to the power of a half is equal to 2 multiplied by 1 take away 3/8x take away 9 over 128x squared take away 27 over 1024x cubed dot dot dot, and this then simplifies down to give us 2 minus 3/4 of x minus 9 over 64x squared minus 27 over 512x cubed for our first 4 terms. Now, of course, we need to make a reference to the validity condition. So let's do that here. So if you think about the fact that we were expanding 1 minus 3/4 x to the power of a half, use this to help you. We can say that the modulus of 3/4 of x must be less than 1, so we can multiply by 4 and divide by 3 to give us the modulus of x is less than 4/3, or written in this format here, x is between negative 4/3 and 4/3. Now, you can also identify that information from the original question. I'll do that over here. If you look at the original expansion, it's 4 minus 3x to the power of a half. We could have said mod 3x has got to be less than 4, which then gives us mod x is less than 4/3. So the same answer. So the expansion is valid for mod x less than 4/3. So, third example, a little bit harder. We're going to expand 3 minus 2x squared all to the power of negative 2 up to and including the term in x to the power 6. So, let's start looking at this. First thing to notice, of course, is that that is not 1 inside the first part of the bracket here. We need to rewrite this. So we're going to take 3 minus 2x squared all to the negative 2. Put in the large square brackets of clarity, and let's take this bracket here, let's take out a 3, and then inside the bracket we want 1 take away 2/3 x squared. Again, all of this has to still be raised to the power of negative 2. So this 3, first of all, we can write as 3 to the power of negative 2, and then 1 minus 2/3 x squared all to the power negative 2 as well. Now, what is 3 to the power of negative 2? It's a 9th. So we have a 9th of this expansion. And let's perform the expansion term by term. So we are taking just this green part here, 1 minus 2/3 x squared all to the negative 2. Now, what is our value of n? Well, we can see n is equal to negative 2. And what is x here in our expansion? Well, hopefully you can see x is negative 2/3 x squared. So we're going to have to be quite careful as we do this expansion. So let's do this. Our first term is 1. Then we want plus n multiplied by x, which is our negative 2/3 x squared. So this second term here will have a power of x squared. We then want plus n multiplied by n minus 1, which is negative 3, multiplied by negative 2/3 x squared, all squared. So this will give us an overall power of x to the 4. So we have to keep going. And of course, this needs to be over 2 factorial. And then we want one further term here, -2, which is n minus 1, n minus 2, and it will be -2/3 x squared raised to the power of 3 all over 3 factorial. Now here, when we work out our power of powers, x squared all raised to the power 3 will give us our term in x to the power 6. So we don't need to carry on working out any further terms. We just need to simplify everything we have so far. So working these out carefully, we get 1 plus 4/3 x squared plus 4/3 x to the power 4 plus 32 over 27 x to the power of 6, etc. Now, of course, all of these have to be multiplied by this factor of 1/9 at the beginning. So I'm going to say 3 minus 2x squared, all to the power of -2, is equal to a 9th multiplied by 1 plus the 4 terms here that we have just worked out. Let's perform the expansion. That's 1/9 plus 4/27 x squared plus 4/27 x to the power 4 plus 32 over 243 x to the power of 6. And there is our final answer. Now we're going to finish off by thinking about the validity conditions for this expansion. So we can look at this version of the expansion and we can say we want mod of 2/3 of x squared to be less than 1, which you can rearrange as we've done previously to say that mod x squared is less than 3 over 2. Now, we've been in a situation like this with an example previously where we can ignore the modulus sign because, of course, x squared is always positive. So we could just say x squared is less than 3 over 2. Now, be careful because this is a quadratic inequality. So you need to do something like sketch a graph to check whether you've simplified this correctly. So here's my quick graph sketch. Here's my graph of y equals x squared. And I'm going to draw on my line of y equals 3 over 2. Now we know that the graphs intersect when x squared equals 3 over 2, so when x equals these values here, plus or minus root 3 over 2. But we want to know when x squared, i.e. the blue graph, is less than 3 over 2, the green graph, so we're looking at this region here. Now this region is satisfied by these values here, so the validity condition is that x is between negative root 3 over 2 and positive root 3 over 2. Or if you want this in the format of a modulus, mod x is less than root 3 over 2. And if you want to, you can rationalise the denominator here. So we're going to end with a very quick summary of what we've learnt so far. Now we can use this formula, 1 plus x to the n equals 1 plus nx plus n minus 1x squared over 2 factorial, etc., to perform any binomial expansion for any value of n. We've also learnt that if n is a positive integer, then this expansion will result in a finite number of terms and will be valid for any value of x. Now, if n is anything other than a positive integer, so for instance if n is a negative number or a fractional number or potentially both, then the expansion will result in an infinite series and will only be valid for mod x less than 1. Now, in every example of the expansion, if we're going to use this formula, the first part of the expansion has got to be a 1. Now, if it isn't a 1, we have to rewrite the binomial to ensure that we have a 1 here. So if the first part of the binomial is not a 1, we have to try and rewrite it. So for example, let's imagine we were trying to expand a plus bx to the power of n, where a is not equal to 1. So, as we've done in the previous examples, we would have to put in our large square bracket like this. We then take this part here, a plus bx, and we factorise out the a. So we have 1 plus b over a x. Each part then needs to be raised to the power of n. So this factor here, a, is raised to the power of n. And we then have this part over here also raised to the power of n. So we now have a 1 here. Now, what about validity conditions? Well, we want to ensure that mod of b over a x is less than 1, which then rearranges to give us mod x is less than a over b. Now, that can also, of course, be written as x being between negative a over b and positive a over b. Now, don't memorise this like a formula. Make sure you understand and learn the theory behind this process.